Hello together. Today I want to explain the scattering parameters. In the lecture before we already defined the wave amplitudes, for example A1 and B1, or A2 and B2. We use the transmission line, and now I want to explain in a first step now our parameter S11, which is a one port, and here I sketched the symbol of a one port. We have the incident wave A1, which will incident onto the one port, and then we will have the reflected wave B1, which will come back from the one port. And as an equation we have B1 is defined as S11 times A1. But what does this one port mean in a transmission line model? In a transmission line model, the one port is essentially a load impedance which terminates a certain transmission line. And here in our transmission line is described by the parameter ZC by its characteristic impedance. And of course, to excite a wave, we need a voltage source, and this voltage source will excite a wave which travels onto our one port, and we call this A1. And of course this wave A1 will be given as the incident wave, so of course this voltage source will emit a wave into our transmission line, and this wave we call the incident wave, and A1 is defined like this. We already discussed in the lecture before. And of course now there will also be a reflected wave, because our transmission line is not terminated in its characteristic impedance. So we will also have here a reflected wave B1. So, and of course this reflected wave B1 is connected to the reflective voltage, and as a reference plane we take especially this line. This means the reference plane is the end of our transmission line. So we have two waves, one B1, which is a reflected wave. Of course this reflected wave will run back to our generator and will be then converted to heat in its internal resistance. And we have the second wave, or the wave A1, which is described by the incident voltage. So this source will create an incident voltage which will propagate to the load impedance. So according to this equation here, we can say S11 is equal to B1 over A1. But if you use these two equations, you will see that this is essentially the reflected voltage divided by the incident voltage in this reference plane, and this is nothing else but the reflection coefficient of our load impedance. So we find that if I consider one port which is equivalent to a load impedance, then we can calculate the parameter S11, which is equal to the reflection coefficient of our load impedance, and this is the equation we can use now to calculate the parameter S11 if a transmission line is terminated with a certain load impedance. To go on in our lecture, I now sketch the symbol of a two-port. So in case of a two-port, of course, we need S matrix or a scattering matrix to describe the total two-port. And here are the equation we use to describe a two-port. That is B1 is S11 times A1 plus S12 times A2, and B2 is S21 times A1 and S22 times A2. But what do these elements now stand for? What is the meaning of the elements? So again, I sketched here the symbol of a two-port, and of course again I sketched here what it means in a case of a transmission line. In the case of a transmission line, this two-port is essentially a quadrupole. And this quadrupole is connected to a transmission line with a certain characteristic set C. And to generate now the wave amplitudes A1, for example, I need here a voltage source. And this voltage source will then generate the wave amplitude A1 here. Of course, if as soon as I have a wave amplitude A1, in general case there will be also a wave amplitude B1 which will be reflected by our two-port. And of course we can also assume that there will exist a B2 wave amplitude B2 which will be emitted out of port 2 here. And now we come to the definition of the elements. You see that I can calculate using this equation, I can calculate S11 as B1 divided by A1. But this is only the case if A2 is 0. So this is a very important point now. Here we must assure now that A2 is 0. So if I would connect this again to a certain transmission line, so then to get no reflections back now in our two-port, I need to terminate this for port 2 into the characteristic impedance of our transmission line. This means S11 is the reflection coefficient of port 1 if port 2 is matched. So it's very important that here port 2 has to be matched, which means we have to connect to port 2 here the characteristic impedance of the transmission line, and as soon as the port is terminated in the characteristic impedance, no A2 will be reflected back into our port. On the other hand, of course, as soon as I have again generated the wave amplitude A1 by this source, then also we will get a transmitted wave which will be emitted out of port 2 here. And again here you see that S21, which will be described the transmission from port 1 to port 2 here. So it's the transmission from port 1 to port 2. And again, this is only true if port 2 is matched. So again here, this condition will alter here the output. So you have to connect to the output the characteristic impedance of our transmission line, and this results in the matching of port 2. So to go on in our consideration, I now sketched our configuration in a different form, and this results from the consideration that, for example, S22 can be calculated by B2 over A2, and also here in this case, of course, A1 must be 0. So what does this mean? Of course, if I want to realize a wave amplitude A2, I have to connect to port 2 a voltage source. Of course, this voltage source now will be responsible to create a wave amplitude A1, which sorry, not A1 but A2 I call it, which enters in our 2-port at port 2. And of course, again, there will exist then at port 2 a reflected wave in general, which we call B2. So S22 will be B2 divided by A2, but again, we have to assure that A1 is 0, so it may not enter any wave into port 1, which again means that we have to connect to port 1 the characteristic impedance ZC. Of course, the characteristic impedance ZC will result in the fact that no reflections occur and there will exist no wave A1, even though there may exist a wave B1 here, which is the transmitted wave from port 2 to port 1. So we can now define the next element. Oh, sorry, no, this is correct. The next element is the element S1, 2, and we have here this element is given by B1, which is the transmitted wave amplitude, which results of A2. So here we are, and again we have to assure that A1 is 0, which again means that port 1 has to be matched to the characteristic impedance. So now we can describe the meaning of these parameters as 2, for example, is then the reflection coefficient of port 2 if port 1 is matched. And as 1, 2 is the transmission coefficient from port 1 to port 2. So we have again a transmission in this direction here. And again we will have that, or we must assure that port 1 is matched. So the matching of port 1 is done by connecting ZC to the port 1 of our 2-port. So in our last step now, I sketched here an arbitrary endpoint. For example, this could be a transition from a coaxial transmission line onto a rectangular waveguide, and also there could be involved a circular waveguide and so on. So we have not only 2 ports, but we will have n ports here. And of course, at the moment I did not sketch an equivalent circuit corresponding to transmission line, but I only sketched here the scattering matrix of our n port. So the scattering matrix of our n port will be a capital N times capital N matrix. So B1 will be S11 times A1 plus S12 times A2 and so on. And so you end up in this matrix which has the dimensions n by n. And now again we can think of what is the meaning of the elements. So we have these elements here where the ports are identical, E times E, so S11, S22, S33 and so on. So this element is given by the ratio of the reflected wave at the same port to the incident wave on the same port, but we must assure that all other ports must be matched. So again here we must match all other ports. So what does SEE mean? It's a reflection coefficient of port E, if all other ports are matched. In contrast, there are parameters which have different index here. So say this is J and E. So what does this mean? We have to measure the wave amplitude BE and divide by the wave amplitude AG. So this describes the transmission coefficient from port G to port E. So we have the transmission in this direction again. And again we must assure that all other ports are matched. So now this finishes our consideration just talking about the meaning of the different S parameters.